So let's get on with mass storage today. Last session we talked about project 2 of project 3 of Windows virtual memory. Hopefully you are all kind of okay in the PA2. After that, just start PA3 right away. There's no need to wait. You don't need to wait for any code or anything. You just, because that was something that on PA2 someone told me that, yeah, we didn't have the code. Well, the code doesn't change basically. We'll provide you for some parts of the solutions, but those are not the things that you're going to like work on the PA3, okay? So, and then make sure you keep updating your code on AutoGrader. If there is any issue or something, again, at least now we have enough time to check into the grader, whatever, or fix it. Please don't do that on Friday. Yeah, because it's just like a lot of groups, and if there's an issue, it most probably will be for others as well. So then it's just like going to be hectic. All right. So today we're going to talk about mass storage, and more specifically, we're going to talk about a little bit about magnetic disks, hard disks, and how they're organized, and some of their performance metrics. And also we're going to talk about disk scheduling, some of the algorithms like first come first serve. SSFT, scanon. We're going to take a look at all of them. All right. So the first thing is the mass storage. We've talked about it before. There are layers of mass storage, and basically you have like cache at the CPU level, and then you have like your physical memory. I mean, even cache has like multiple layers. And after the physical memory, you have secondary storages, right? So those can be like magnetic disks, magnetic tapes, SSDs, flash, whatever. And so magnetic disks are really popular, and up to a few years back, they were almost the only kind of secondary mass storage for everyone, at least commercially. And so they have they're a little bit slow, and their transfer rate is again much slower than physical memory, but at least they provide robust. They're non-volatile, so your data won't like go away unless you pick a magnet, move it around your hard disk. And the other difference between them and, for example, physical disks is that they have less data rate when you're reading randomly. Right, because we talked about it also last session. Your arm has to move around. You have to like read from one sector to the other sector. If it's like far away, there are like physical movements that just takes time, and that's not true, for example, for SSD. For SSDs, the technology is like electronic, so it's kind of like how you think of memory. So you give the address, it gives you the data. It doesn't matter if it's the same or close to the previous one or not. It's just like goes on, right? And it is much faster than the magnetic disks. Again, the same type of I/O that is, it is still considered as a secondary storage, but it is like much faster with like newer technology. All right, but again, it comes with cost. So, for example, one is it's much more expensive. It is becoming less expensive, but relatively, but it's still much more expensive. I was actually going to buy one. And yeah, it's at least 3 times maybe more expensive or more. Another problem with SSDs, who can tell? Yeah, Phoenix. The lifespan is shorter, and
you only have a limited number of writes.
Yeah, so that basically turns into lifespan. But the problem is that the lifespan doesn't degrade. There is no middle, state. It just dies. And I lost a lot of data just like that. It was like, end of the semester for me, literally given 1 more week, and I had like plans. So I usually take backups. Do it, really. You don't know when it strikes. And so I just like had some of the stuff that I meant to back up on my desktop. Couldn't wait for another week. So, and then that's the problem with magnetic disks. If they start failing, they start making noises. They become slow. They have like bad sectors, but you can retrieve other sectors. You can just like do something. You can see it coming. Solid state, no, it just dies. And you can even, they have like banks in them. But the problem is, like, once it's just like failed, you cannot even retrieve those data in the banks, unlike the magnetic disks that you can take the, those platters out, put it on another disk, whatever. Solid state, no, that's it. Yes?
What about PCIe, NVMe, M.2?
What's that?
Faster than SSD.
Okay.
It's different.
NVMe, non-volatile memory, what is that?
PCI storage, like
Oh, yeah, I've seen, I don't know if I've seen it, but I know what you mean. Okay, yeah. I'm not sure about the technology, if it's different or it's just like the same, but a little bit faster. I'm not sure. Anyways, so they have like, their pros and cons. And so we also have magnetic tapes. How many of you have seen them? Where? In a museum? No, seriously, where? Nice. Okay. Yeah. Those are cool. So these are like gigantic tapes. The technology is similar to the magnetic hard drives. It's just like that they roll, so there is no arm. You cannot move. There's no random access. You have to start and then just like keep rolling, just like an old cassette tapes if you had one. Again, especially the random access is much slower. Once you are at the position that you want, then you can just like read in sequentially, kind of like magnetic disk. The storage capacity is much larger. All right, and they're usually used for backup, archives, whatever, data centers, type of data that might not be used frequently. All right. So now, again, this is the hierarchy. Storage management, starting from the registers all the way to the magnetic tapes, and also it's not exactly necessarily just like that. So you don't necessarily put magnetic tapes data on optical disk and then bring it to hard disk. No, you probably can have them into memory as well. But this is the way that you move your data as you want to store them or use them more frequently, right? So whatever that you want to save, then you save it on your hard disk. And then if you want to now back up some of your information, you might write it on a Blu-ray. And then if you are, or if you own a data center, then you can actually back it up on magnetic tapes. All right. And as you move down, you go to larger capacities, slower accesses, and then you basically have just dropped. All right. So as you move down, you just like go towards the files that are like larger and inactive. So you never have your system files obviously on these, right? The smaller files, more frequently used, always up. All right. So now let's take a look at this image, which explains the magnetic disk. So a magnetic disk inside, it has some platters. And so these are just like coated with some magnetic material that you can store the orientation of the north and south pole. And then there is a physical like arm assembly that can move, and as it moves, basically it can like cover a different circle with a different circumference, right? And then, so it starts like this only can spin enough so that it can cover a different circle on, or as they call it, like a different track. And then once it is on a track, then the platter itself starts spinning, so a different sector like this can come and just move around underneath the arm, so the arm can read it. And we don't have necessarily one platters; we have like multiple platters. Now, when the arm moves, all these arms are looking at parallel same size tracks, but they are called a cylinder, all right, on different platters. Okay, so this basically just shows how it works. Whenever you want to read a sector, go ahead.
So the sectors, like in you're looking at the physical disk, would it be like a very minuscule circle?
Come again?
In the sector, would it be like a very minuscule circle on a physical disk?
A sector is not a circle. A sector is like a. Oh yeah, tracks are circles. Yeah.
So just like bit by bit.
Yes. So this is a little bit also different than how, for example, gramophones work, right? Those are also platters, right? But they are not like circles. They're one single track, which just like spins, right? Oops. Probably not noise. So these ones are not like that, though. These are just like circles, and then the arm moves on a track, and then so. And so if you want to address a sector, basically that sector has an address. It resides on a track and a cylinder. Basically, a track and a cylinder. So cylinder basically defines which one of these is which one of these circles, and the track like points to which one of these platters. And so basically the sectors are the minimum unit of transfer. So usually, for example, we say like it's 512 bytes, and the hard disk can basically write a sector or read a sector, and at the same time it does some calculations to the data on the sectors, right? So take a look. So each sector has a header. It has the information, which are like the bits or bytes, and then the error correction codes at the end. So every time you write something on the sector, the normal I/O, the I/O controller of the hard disk itself calculates the error correction codes and write them as well. So next time, whenever you read a sector, it also again calculates the error correction code, compares it with the error correction code which is already there, and if there's a mismatch, then it's like a error, and then it either lets the lets the OS know about it, or handle it for itself. So, for example, depending on the error correction code, if the error happens like in a single bit, usually they're recoverable. If it's something more than that, and they cannot recover, then they have to now either skip a sector. It's called a bad sector, basically. And so there are various methods to do that. So the first of all, the header itself has enough information about that sector. For example, what is the ID of that sector, and the other thing is like this flag. So once the I/O controller knows that the sector is bad, there are various ways to get around it. So one is like forwarding. So even though you think like during normal I/O controller you think that this header is being used, there are reserved sectors somewhere else. And then any bad sector can get basically forwarded. So there's whenever you ask for this sector, it just goes back to the table, reads it from the bad sector reserve. Or sometimes they have they skip sectors. So it starts from this one instead of this one. If it's not usable, it's just going to go to the next one like that. All right. So and some of these will be handled during with specific I/O instructions. For example, when you do low-level formatting, if you've heard of that, which takes usually much longer on a hard drive. Not even the formatting. So even sometimes when you format a partition, that's different. You have quick format and full format. So quick format is only basically formatting for example, the file allocation table in the case of FAT, right? The file system. It only formats that as if it doesn't wipe the data, it doesn't change the data on the hard disk. That's why the recovery program still can, retrieve the data because the data is there, but the table of the file system thinks that, okay, it's free. And that means it's usable. So you think that it's, usable and free and, you have all the space, but if you don't overwrite them, the data is still there. So if full format, it starts writing all the sectors, but again, usually it's just normal I/O. And it doesn't change, for example, the sector size. However, a low-level formatting is it goes into different sets of instructions that allows to talk to the I/O controller a little bit more directly and ask it, for example, to leave more bytes between the header and the error correction code, and change the sector size. It has pros and cons, obviously. You have more data for each sector, so less waste on header and error correction code. But on the other hand, you have internal fragmentation in each sector, and if you lose a sector, you lose more. Yes. What's that? So if you have a bad sector, right, then you're going to skip the sector here. So if this is sector 1,000. 100, and then this is supposed to be 1,101, but if it's a bad sector, then the ID of this sector will be 1,101. So whenever you're looking for that it automatically basically skips it. So whenever you have like, sequential sector reads, right, it finds one and then starts reading. So, after reading, like, let's go to a different number. If it's 60, this is like 64, then it expects that the next sector is 65, right? Now, once it reads this, it realizes, oh, it's a bad sector, so the 65 will be next one. It just skips this to the next one, alright? If you actually forward it, if you want now to read sequentially after 64, you realize that, 65 is defective, so where is 65? It's somewhere else in the drive, so that takes time. But this way, for example, if you just skip and move on to the next, it's just like faster. But on the other hand, it requires either prior knowledge or some gaps in between, because before this going defective, this was 66. So now that it has been defective, if you want to move 65 to this, then you also have to move 66. So there is, either you have to have like some gaps or something. It's just like different methods. Alright? So, how about performance? So whenever we are talking about magnetic disks, there are different metrics that we talk about. So the first thing is disk latency. Whenever we say disk latency, it's an average time that is for positioning time and transfer time. Now, what are each of those? Let's see. So the positioning time is for the time that you send a request to the hard disk to, I want that sector on that track, until it can actually start reading and transferring data. Right? So it consists of, and it's usually an average for random access. Otherwise, the positioning, if you just want the next sector, is almost zero. So it has two components. One is the time to move the disk arm to the desired cylinder, and then, which is called seek time. This is called seek time when the arm moves back and forth on the platter. And then, the time for the desired sector to rotate under the disk head. It's just called rotational latency, right? Going back to this, so the ARM assembly can like seek from this to this track, but it cannot read this sector here. We still need a rotational movement of this spindle to move that like a sector under that arm head, and that is called rotational latency. So this one, positioning time, is combined and it's an average, right? And so the rotational latency is a function, for example, of how fast the RPM is. Usually you've seen like 5400 or 7200 RPM, but also it might not be constant. So, for example, all geometry, right? So, and physics. So, if this has a constant rotation, what will be the difference between the inner tracks and the outer tracks? Yeah.
You can read more on the outer tracks.
Well, technically you can't read more, because then you will read less on the inner tracks, right? Yeah. So if you wanted to like have the same behavior, there are like multiple ways to do it. Either you have to change the speed of rotation, which is, for example, something that you might see in CD drives. They like spin up and spin down because that's like, where the data is going, right? So the problem again is, if you're reading on this track, each rotation it's just like because of the diameter and circumference of these circles, you have more space on them. So let's say you have more, if using the same density, you have more data on them. So basically each rotation on this takes, let's say, 100 sectors, and then each rotation on this takes 150 sectors, if you have the same density of material and bytes on them, right? So if you are reading, if you keep the constant rotation, then if your arm is on your inner circle, it's just like, it's moving more slowly than if it's like on the outer tracks. Now, again, for example, drives, sometimes they change the speed based on where the arm is going, so that always, wherever the arm is looking on the platter, it's just like reading at a constant rate. The other way to do it is change the density of material. So each sector, for example, can be a little bit, stretched on the outer tracks. So, going back to this. So, that's why the rotational latency, you don't have to calculate it for different tracks, but it's just like an average. Now, the transfer time is the time to transfer data onto and off the disk. Like that arm head on the platter, like takes some time to swap or rewrite a byte, and that just like takes time. And the transfer rate is the rate at which the data flows from the hard disk to the operating system. Again, this is two rates. You have one rate from the magnetic platters into the hard disk buffer, and then one rate is from the hard disk buffer to the operating system. And these have the different data rates, because that one has to do with the bus, whether it's like IDE or SATA, whatever. The other one is just like the inner structure of the hard disk. And we don't usually talk about this, but you can also have a crash between the ARM and the platter if the disk, for example, is damaged. And that is one of the reasons that they say, if your hard drive is spinning and working, don't move around your laptop, don't give it a shock or something, because this can happen, and then that will basically damage the hard disk. So this is an example of Toshiba disk. Let's take a look at this and put the phones away. You usually have a number of platters. This is the data sheet, on the specification. And then you always know the capacity, but these are the things that now we are interested in. So the speed at which the hard drive can spin, the average seek time for read and write. Again, for read and write, the seek time doesn't change because the ARM just needs to move. And so sometimes it is. I think this can be an average, and I don't know why there are two numbers exactly. I think for read it can be smaller than write. I think the reason is that they just embed the extra time needed for write into the average seek time. Otherwise, the ARM itself moving doesn't change. Yes?
It says 2 platters, 4 heads. Does that mean it's writing to both sides of this?
2 platters, 4 heads. I think it does. I think I haven't actually checked that, but I think for each platter you can have an ARM above it and one ARM under it. So you can have double coding. So then there's maximum seek time, 19 milliseconds. That is probably from the most inner track to the most outer track. And track to track seek time is 1 millisecond. This is basically the minimum time. So even though you have many tracks, which it takes 19 milliseconds from one to the other, you can't just divide that by the number of cylinders and then say, okay, if I just want to move from this track to the next one. No, it has a minimum, because again, that ARM has to kick start and start moving or whatever. So this is just like that. Then there is a surface to buffer the transfer rate, which is a little bit slower, but then you can actually cache it into a buffer, and then during an I/O burst of operating system starts reading those, or probably that actually happens using the DMA. But anyways, so then there's the buffer memory, which you can ask whatever that you read from the hard disk. It just buffers it, caches it, and then at some intervals empties that. And of course the power. All right? Yes.
How do you access 2 different things at the same time?
You can't. On 2 different, for example, data or sectors.
Yeah. So on a magnetic disk, if you have 2 data, 2 different locations.
No, okay. Depending on we're going to take a look at the scheduling algorithms. You might be a little bit smarter. So if on the way of this data, you're already passing this data, you can just read it and then keep it in the buffer, This is something that has to do with that. Not sure if the disk I/O controller itself can also do something like that. Yeah. But normally it's just you got to think of it as one by one. So this is an example. How long to complete 500 random disk reads in FIFO order? A couple of numbers here. And how long to complete 500 sequential disk reads? What is the difference, and how to calculate that? Just give it a minute, think about it. You have been given the seek time, an average seek time, an average rotational time, and then we have the transfer time for each sector. And then it's asking for 500 random disk reads and sequential disk reads. Give it a minute. Think about it. Now, if you want to raise your hand, just go ahead. How to calculate this one? Go ahead.
So, rotation as transfer
Mm-hmm.
times 500.
Mm-hmm. Why? Okay. So basically, we have a delay. We have a seek time. We have rotation latency. We have transfer time, and
plus seek times 500.
okay. So why is that?
We don't know where it will be, right?
Okay. Okay. So what's the difference between this and this then? Mm-hmm. So it's not just seek time, but it's also rotational time. But you're right. So in order to actually go to the first sector, right, you have a seek time and a rotation time to get there, and then you have to read it, which is the sum of all of this. So now when you have like 500 random disk reads, that means from this sector to the next sector, you might do the exact thing, same thing again. So you have to seek again, you have to rotate again, and you have to read again. And again, for the next sector, you do this and this and this. So for this one, you basically have to seek, rotate, and then transfer for every sector, 500 times. How about sequential disk reads? Sequential disk reads means when you get to the first sector, the next sector doesn't need seek time or rotation time. It's just like, after that, right? So the rotation latency is an average of sectors. It's not when you are reading two sectors one after another, because if you actually read a sector, then you are at the next sector. So the rotation latency is an average for the whole track. Okay? So this one, basically, again, all the latencies added, multiplied by 500, you get the number. This one, you have 500 transfer times, because all the sectors are one after another, but you only have to seek it and rotate the platter only once. And the difference is huge, right? So this is, for example, why random access and sequential access is so important, and whenever they advertise SSDs, the random access time or sequential access time doesn't matter. So this is because of this. And a lot of time you can't help this a lot because of, how the file system works. So you have random accesses, not necessarily every time like that. Again, like last week we talked about it. Usually the file system tries to put as like clusters or blocks close to each other for a single file, because whenever you read the first part of the file, it's, easier to read the rest, right? But again, sometimes it's just like not happening. All right? Yeah.
Isn't there still some seek time if we're moving to a different track? If we have 500 reads and they're on different tracks, we still have to seek at some point.
Technically, yeah, but we usually don't count that. Yeah. But it depends. For example, like if all the I'm not sure about the number. For example, how many sectors are in a single track? If it's less than 500, then you definitely need that, right? If its number is like, let's say 50, obviously, then you're like changing a track like 10 times, right? Then that actually 10 milliseconds is comparable to this. But if there's a chance that you may skip a track and, you do it once, then it doesn't matter. All right? And I'm really assuming that there's more than, like, the order of sectors on a track is not that small.
Yeah, probably.
Yeah. All right. So how about scheduling? So now, just because of what we saw here, right, it matters that we try to at least eliminate as much as possible from the seek time and rotation time to avoid all these latencies, right? So what we can do as the I/O controller of the hard disk is something. What we can do as the operating system is a different thing, right? So we are taking a look at the disk scheduling, and that is if the operating system knows that we need to read a bunch of data, can we manage it a little bit better so that, because as you said, we're gonna like basically read them one by one. We're gonna like submit these requests to the IO controller one by one. Can we do it a little bit smarter and save some time and do it more efficiently, right? So it basically the components that are like hurting us the most is the seek time and the rotational latency, and the overhead of the scheduling and all the other things is usually, again, negligible compared to these, right? So what we want to do is to minimize seek time, and the seek time is relative, or like almost equal to the seek distance, right? So the rotational latency, by the way, if you take a look, where's that? It's usually like smaller than seek time, because the head is already spinning, pretty fast, and but the seek time moving the arm can, take a longer time. And the rotational latency is an average number, and at any given point, it might be like difficult to predict, like it's like at which angle it is, so that you can. But the seek time is different. The seek location, you can tell if the arm is on this track, 1 millisecond before, 1 millisecond after, whatever, the arm is there. So if you want to move to a different track, you know how much you have to move. But the rotation, again, because it's just like keep spinning, 1 millisecond before or after, you have a different idea of what's going on. Okay, so the algorithms that we are going to talk about is their goal is to minimize the seek time, and again, because the arm moves on the platter, the seek distance is what when we talk about. So the tracks have a number. I think their number actually starts from the outermost track, but it doesn't matter. You can either have it like from 0 to, from like the inner ones, or 0 from the outer ones. Now, if you want to move your arm on these, basically, based on the request on each track you want some data, the distance that your arm has to move from one request to the other one changes, right? So let's take a look at a couple of examples. For each of these algorithms, we're going to go through an example, and we're going to talk about them, right? So all of them basically is like the request that we already have. So let's say for some reason either one process or different processes, they have requested some information, and again, through the file system, we know the blocks that the information that they need reside on these locations. And again, these are not sectors, they are tracks. Okay? So there is a one sector on this track, so once we move to this track, it just rotates and that sector comes and we read it. We don't care about that. But we need to move between these tracks in order to get all these data. Okay? So, and we also have, currently, let's say you have an initial status, which is, from your previous read. So in these examples, our arm is on like track number 53, and we need some information on these tracks. All right. So let's take a look. The first one is first come first serve, right? And obviously, you know what it means. It means that these queue that you have to first go and read this data, and then go and read this data, and then this data, and then this data, and then so on and so forth, right? So how would the performance look on the first come first serve? So the first thing is that we are on track number 53, right? We are here. So if we want to move to 98, how much of a distance or how many tracks are we moving? From this to this? 45. So it moves from 53 to 93 to 98 and moves basically 45. Then from 98 we need to move to 183. That's about 85, right? So 85 and 45, add them up, that's 130. You just like keep adding them, right? So from 98 we move to 183. And then from 83 now we have to move back all the way to 37. Again, just think of this platter, the RDX platter. We have like done it like this. We have rotated it like that. And now the arm is like this, moving between these tracks on the platter, right? Back and forth, and this is spinning, and we're reading data, okay? Now, we're taking a look at how much movement we are making. So on FIFO, FIFO first come first serve, it's like simple to understand, but it's just like also know how bad it is doing, right? So from each track, it's moving to the next track, this track, this track. It's moving all over the place basically, and it's just like, taking a long time for each of them, which is unnecessary, right? So this is first come first serve, and overall, like for this example, like it's moving for 640 cylinders. So first come first serve is easy to implement. It's easy to understand. It is fair among the requests. If a process or has sent a request earlier than the other one, it will get its data earlier than the other one, right? It's as simple as that. However, it can just like because the request might be just random, and then the seek time, at least again, we're not talking about the other latencies, but the seek time itself can be terrible. All right. So, and again, this might not be the case for SSDs. SSDs have their own issues. We may talk about it slightly after this. So the next is shortest seek time first, right? So shortest seek time first, like this, the name already tells it, right? So if you have a bunch of requests, you first serve the one that has the shortest seek time. And yes.
Would that be like the shortest from the current location, or the shortest like from 0?
Well, you want to minimize the time, right? The time it takes your arm to move from current location to there, right? So this is what it tries to do. And it already sounds like the shortest job first scheduling algorithm, right? The same, like, behavior is like expected, right? It is actually tries to minimize that, and then it reaches that, but with some, cons, right? So let's say for the same example. So if we are at 53, which one of these we're gonna like look at first? 65, right? The 53 to 65 is 12, so we just like go from here to here. After that, which one? 67. After that, which one? 37. That's 30. Between 67 and 37 is 30. Between 67 and 98 is 31. So yeah, we move to 37. After that, we move to 14. After that, 98, and then to 122, 24, and the rest. Okay? So this is just like, and then it reaches the minimum seek time for these requests, 236 cylinders. What's the downside of it?
I can't remember the name for it, but it's like a priority schedule. There can be hang-ups and keep adding to the
Starvation, yeah. Yeah. This is true. Right? Yeah. Well, that can happen much faster than the seek time. If you save 2 milliseconds here, you can run thousands of instructions on the on the computer, on the operating system, and everything. Well, still with a good data structure, for example, or algorithm, you can still like if you have an ordered list, and then it's easy to get that. And we actually get to a couple of algorithms when we have a lot of requests, as you say, right? It depends on the load. So not every algorithm is like the best. Otherwise, we would only have like one algorithm, right? So the pros is that it tries to minimize the seek time, and it is again, I think it's the same as the shortest job. It's just like proven. But the problem is that it has a starvation for some of the requests. Let's say if two processes are like sending requests, together, and then for some reason we are now at this side of it, and then the other process just throws requests there, and then this one throws requests. As long as we have another request there, we're not going to move there, right? So that process is just going to basically wait forever, right? So this is the problem that the operating system at least should handle, even if you're like trying to like have this shortest job, shortest seek time first. You may want to like come up with a heuristic to at least every now and often sweep around, do something else. And then we get to that sweeping actually in the next example, right? So the next one is a scan. So a scan, yes.
So like if we have two equal
Yeah. Yeah, tie-breaking. It's always a question in any of the algorithms like that. But usually we say, for example, keep moving the arm as it was. So if your previous location was here and you move to here, and then now you have two requests equally distances, just keep it the same direction instead of twisting that. Hopefully that won't be at least on this, our examples. So the scan algorithm is like as it says. It basically scans the platters just like back and forth, right? It just like goes back and forth, and it's called like an elevator algorithm because it just like goes all the way up and then all the way back. All right. It goes as it reaches each request. It has it sorted, so it just like picks them along the way basically, right? So it's simple to, I guess, grasp the idea. If you are 53, let's say we are moving up or down. Again, this is something that you need to know beforehand, know which direction. But in this example, we're moving down, and then all the way to 0, and then again moving up, all the way to 200. And in this time, we're assuming there's no more requests coming. So, basically, we get 53, we get 37, we get 14. We go back to 0, we come all the way back up to 65, 67, 98, and so on and so forth. Okay? Yes?
Do you have to hit 0 if there's no request there?
If you're implementing a scan, yes. We're going to take a look at the better version, which is basically, something that makes more sense.
The lowest numbers and you start going up?
Yeah, that would be look. Alright? So, this one doesn't care about that. And just keeps moving like that, and again picks them up. On the other hand, one of the reasons is if your request was only 37, and then you didn't want to move back, and then what if in the meantime a request would come here, and then you have to wait for it all the way to go back and forth, right? So it changes some of these corner cases basically, but maybe on average, that's not the case. So this is similarly to, scanning all of them. Actually the C scan would be more like that. But still, you have a bounded service routine time, right? Because if you think of it, it's just like no matter how many requests or on which track it is, you have the arm will move back and then come back at some time, right? So this is similar. Again, this and the next one will be similar to the round robin scheduling algorithm because you know that you will have your turn after n-1, right? So the problem is now some of the requests are they take longer than the others. So especially if you consider this request, for example, if the head moves from here and then back to here, it's 106 cylinder moves. Now, however, if you're from 0, once the platter moves away and then all the way comes back, it's now almost 400 cylinders. So even on this cylinder now, on the one side is 106, on the other side is a different number. So it's just like that. It's not, it's not uniformly. The latencies won't be uniformly. So that's one of the cons of it. So any questions in the scan? All right. So the C scan is circular scan, and it basically folds the platter logically, wrap around itself from say inside out. So basically, instead of going all the way always from 0 to 200 and coming back and picking all the requests, it considers that I'm always picking up, on the way up. So it goes from 0 to 200, and then comes back to 0, and then again goes up to 200, and then again comes back to 0. Now it has a couple of pros and cons by itself. So remember that you can't still jump back from the 200 to 0, right? You can't just go from 0 all the way to 200 and then start 0 again. That still needs some seek time to move the arm. But the fact that you're not picking data up on the way will make it much faster. You have one seek time from that to here, and then again starting over, right? So this kind of helps that the problem that scan had, which was treating different tracks differently. If they're like in the middle, they have like, some leverage than the ones on the outer or inner tracks. The C-scan doesn't care about like which track you are, which location. You will always have the same latency relatively, for each time. Okay? So again, just remember that this is like, circular, and then starting from the 53 this time, I think in this figure, we're actually going up. So 53, 67, 65, 67, 98, 122, 124, 183, all the way to the end of it. And then we move back to 0 and then pick 14 and 37 up. Okay? Just like that. Now, I think we already talked about the benefits of them, right? So it provides a uniform waiting time, and the constant does nothing on the return. So this is just waste of time when the arm is moving back. Yes?
So is the only reason why it's like better than regular scans that's more fair looking at it?
Yeah. All right. Now, look is the improved version of a scan. So it's the same principle, but instead of like going all the way to the end of it just like goes all the way to the, wherever we need. Depending on the current requests, it's like an actual elevator. If you have like a 10-story building, right? If you hit on level 8, the elevator goes up. And on the way, you can pick people up. But as long as none of them want to go to the story of like, the 9th or 10th floor, the elevator actually doesn't go up. After that, it's just like, goes down, right? So this is like the improved version of the scan. So, in this example again, the 53, we instead of like going all the way down to 0 or 199, we only bounded to 183 and 14. So again, we want to like move up. We have 65, 67, all the way to 183, coming back, servicing this one, and then the algorithm basically is like finished the last request here. That is, by the way, one of the metrics that we want to talk about. I think I didn't specifically mention it. Hold on a second. The bandwidth. The bandwidth is the total number of bytes transferred divided by the total time between the first request service and the completion of the last transfer. So just if you are talking about a total service time, it's just like from starting of the first request to the last transfer. Okay. And again, this is the first request. So if you have to move your arm to get to the first service, that is also included in the time. But in this example, if we already finish at this location, we don't have to count, till the end of it. Alright? So, as we have scan and C-scan, we have look and C-look, right? So that is the same as C-scan, the same improvements that look did to scan, right? So the C-scan was a circular wrapping around the platters, moving from tracks as if the 0 was right after the, last one. And then the same thing is happening. The look goes all the way to the last request, and instead of going all the way to the 200 and then starting back from 0, it goes to the last request and jumps back all the way to the first request, right? So it's just like that. You're not, caring about the head or the tail, right? And again, this is very similar to the C-scan, but it's just saves time from going from here to here and back, and also from going to here and back. I mean, basically going from here to here and back. All right? Any question on these? Yes.
Why would you use scan over book?
So I mentioned an example. When you have a corner case, in this example, if right after changing your direction from here, you have a request above that, then you're missing it, right? And I think also it's simpler, basically. I think the implementation is simpler when you have when you know that, okay, I'm going to go from 0 to 200, rather than making, like, deciding, should I make a turn? Should I make a turn? Should I make a turn? So this is an exercise. We can cover up some of it today. I guess we have enough time. But before going back to this, we're gonna, if there is any specific question on the topics that we covered today, or for your project, we can answer those, and then we can come back to the exercise. All right. So again, type of the questions that you get on these is just like that. You have a request queue, and then you are usually given where the head is here. So assume the disk has moved to it is located from track number 100, and it has moved from 44. That also gives you basically the direction of the previous arm movement, right? And then now if depending on the algorithm, you have to basically calculate what are the order of the request services, and eventually like how much movement of the head it took. That gives you also basically the average, not the average, the total latency. All right. So we're going to come back to this on the board. So now the differences between the algorithms depends on the type of usage, right? So for example, if you have I was going to say, like, if you have a magnetic tape, then you're basically picking up sequentially, so you have to use something like scan or look. But basically, each of them has pros and cons. So if you have like many processes, and then you want like fairness, then shortest seek time is not good for you, right? Because again, two processes at different locations, and they might just like request, and that's not good. If you have like if you want actually performance, and you have a single process, or if you actually care about only one process that you're running right now, then actually this is like the best for that. So depending on the type that the operating system is designed for, or the type of your application. I mean your application. I don't mean your software, but the usage of that operating system. These can change, right? So scan and CScan are better when you have like a lot of heavy loads, because you will have all over the place. You will have requests all over the place. So obviously the first come first serve is going to just be terrible, right? And when you have all over the place, then this is also not good, because it's going to like starve a lot of like processes, like requests that are farther. And so the scan, on the other hand, just like moves around and picks them up. And you're sure that on the way back, you're not losing a lot of, you're not wasting time. So when you have a lot of requests and coming, and then as you go, and then, there are requests just like, that are coming. So on the way back of the arm, you will address them all, and then again, right? The circular also, again, it's just like the same, but it's just like, I think, the only benefit of a circular one over the other ones is that the latency would be a little bit more uniformly. Again, you have to like see if you care about that more or the latency of the arm. Go ahead.
If you're moving the arm like all the way back without reading, though, can you move it faster?
Yeah, that's what I'm saying. Like whenever you're reading the sectors, those need rotation time as well, right? So, like if we take a look at the data sheet that we have here, let me just move a lot of this. So here, in this example, we have some seek time. We have seek time. Here we don't have the latency of the rotation, but in this example, at least the rotation is given as like 4 milliseconds, which I think is not accurate, because if like the rotation is taking one like half a rotation, which is like, if you consider like 5400, that's what, half a millisecond almost, right? So let's say it's like 1 millisecond, but now if your seek time is 10 milliseconds, so each rotation gives you like 10%, right? So if you have 10 read or request on the way back, for each of them, on average, you have to waste another millisecond ignoring the transfer rate, right? You have to move the arm here, wait for the rotation, and then again move it here, wait for the rotation, and move again, wait for the rotation. All these weights will add up. Whereas if you just want to move all the way the arm from 200 to end of the track, basically, to the start, you don't care about the rotation anymore, and it will be faster. Right?
Can you even do it faster in hardware too? Like they can speed up instead of just moving at the normal speed, it moves like.
So that is something that this example kind of shows. So the track-to-track seek time is like 1 millisecond, and the maximum seek time is 19 milliseconds. The average seek time is 10 milliseconds. So this tells you about that, right? So the maximum is, again, because they have to accelerate and decelerate, basically, right? They're physical components. Now, this is the maximum that you need. So whatever track that you want to, like even if they're right after another, this is equal to 19 reads on the way back, right? And if they're not actually one after another, they can take up to, let's say like 7 milliseconds, right? If they're a little bit further apart, but they're not like all the way so fast. So this is actually happening already, and so we are not actually getting into the details of what is exactly number or whatever, but this gives you the idea. Like the average seek time is 10, but the maximum is 19. So you can tell, because the average is not necessarily from the middle to the end, right? This would only make sense if they were proportional. Then the average would be from the middle to the end, right? But that's not the distribution of calculating the average. The calculating of the average is like randomly distributed, and then getting like an expected value, whatever. But that would be definitely the distance would be less than this. However, the time is more than that, and that is because, again, of the acceleration deceleration. So that's why something like that actually makes sense, because you just move ignoring all the rotational latencies and like all the stops and starts. And there's also, by the way, the hard disk have mistakes. They make mistakes, right? So this we haven't talked about today, and we didn't cover. But whenever you ask for a track or a sector, there's a chance that the hard disk mess up, right? Now the expense of that is also now matters, right? So I think, for example, when you are changing direction, maybe the probability of making a mistake and moving to a different track maybe goes a little bit higher. Whereas when you move your arm all the way back, there's probably it's easier to basically find if it's at the starting track, right? And then as you move up, it may make less mistakes. So because every time you ask for a track and a sector, the arm moves there and makes a mistake, great. But it now will figure it out. It reads the sector, it realizes, oh, my arm is somewhere else. Now I have to move back somewhere else, right? And that will probably be close, but again, there's always latency to recover from that error, okay? Now, these errors also add up, and I think maybe one of the reasons that you might want to move the arm all the way back and start over in the same direction might help with that. Okay. Okay, this one is also the other thing. So the file allocation method of the operating system itself can play a role on this. Again, if the operating system knows that this file belongs to one process, then probably if they open one part of it, they want to read the rest of it. So this should try basically to put it closely to close tracks so that the seek time will be minimized. Again, normally if you have low load, then the shorter seek time first makes sense, because that's just gives you better performance. If you have a high load, then the look gives you high performance, because you just sweep, you don't waste time at the ends. So, but the other ones are also there. All right. Any question on these? So, checking on your assignments and then going back to any other questions or the exercise. All right. So make sure you complete your PA2. If there's any issue or questions, just post it on Piazza. Sometimes I see some questions on Piazza which are really not expected. I mean, not that I don't ask them, but I'm saying, like, for example, checking whether you're in the build folder or not is something that you have like gone through the semester so much. But on the other hand, sometimes I feel the students are struggling with an issue they haven't like posted on PL. So post your questions there. Yes.
Isn't the date different? Because I think isn't it this Friday?
Okay. Oh, sorry. Yeah, this is the due date for design document of PA3. I think I messed up. So yeah, this is 19th, this Friday. Thank you. All right. Was that the same arm for that reason? I saw two more. Okay, yeah. I will actually fix it after this. And then the grace day policy, remember that because I have not used AutoGrader with grace policies on, so just expect a little bit of, I don't know, chance that on your grace day when you submit, I don't expect it, but I can't test it. I can actually. Okay, I'm gonna actually bring the deadline today and then try to submit content or something. But just like know that if for any reason you submit to your AutoGrader, even if your grade is not what you want or what you expect, as long as your submission is there, don't panic. It's fine. If it does not allow you to submit for some reason, you don't actually see anything, then send an email to one of the TAs or me, just to make sure that your file is time stamped and we have it. Okay, and if you are done with PA2, start with PA3. All right. So if you have any questions on the topics, if not, we're gonna actually have like 10 minutes or 5 minutes to go over the example and see how you actually start like solving those type of questions. Okay. So I'm just going to go over this page and then go back to the example. Yes. Excuse me, a little bit more quiet, a little bit louder. Yes, I think you already asked this question. Yes, the design document, we can provide it to you a little bit earlier because that's just like, you can actually see the design document yourself. Just ignore the ones that are for swapping and memory map files. What's that? Yeah, swapping and memory map files we're not doing. Alright? So, for whoever like sitting down, I'm going to go over this exercise, alright? If you would like to leave the class, it's fine, but try to do it at least, a little bit more quiet. Okay, so this is, in these type of questions you will definitely see in, exam. So, we have I have to write it, otherwise it will be too bright. So 55, 58, 39, 18, 90, 160. Next is 150, 38, and the last one is 184. Okay? Now, we consider them to be, again, in the line. Usually, it makes sense to have them a little bit more proportional, but it doesn't matter. So, right now, I'm just going to sort them. So, the smallest one that we have is 38. We start from 0. So, let's say 38 is here. And then we have, what's that? Oh, we have 18. I'm sorry. 18 here. Didn't see that. And 38, and then 39. And then, do we have anything between 39 and 55? No. And then 58. What's next? Is it 90? 90. And then you have 150, a little bit farther down here. 160, 184. And I think it also assumes that we have 200. So basically it's 199. And, so just to make sure, sometimes, when you have done something like this, these are just like hints to not to mess up on a, exam or something. Just count them just to make sure you've covered all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9 of them, and you have like 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. So you haven't missed one. Yes.
How long would it take you to go from 0 to 200, while reading each of them?
So it depends. You can calculate between each of this. Usually you consider the average seek time, and so the number is like 9 of them. considering now that you're also at a different location, so that you're at here as 100, so you have to move for each of them once, and you take it on average. And so in this example, we haven't been told what are the times, but the average seek time, you multiply by that the number of requests, basically. Yeah, we don't do any finer than that. So if this like movement is like smaller, I mean technically this is the one track movement, which was like in the example, which was 1 millisecond. But if you want to like go there, then it would be just like too difficult to now separate. Okay, now this one takes longer or whatever. Usually we just like take all the average. Okay. Now in this example, we don't actually take the times. We just like count the number of cylinder moves, right? So we are at 100 at this point, right? And we got to here from 44. So this was our previous one. So we have moved from here to here, right? So it's just like going up. Now, which algorithm we should like pick? First come, first serve, shortest seek time first, scan, C-scan, look, or C-look? C-look? Let's do C-look. So the C-look, you remember, it was circular, so as it's going up, we can tell that it was like, going up, and it's like, the next it will be this one, and then once we get to the end of it, we have to come back all the way to here, not to the end of the track, but to the first one we have here, right? So basically, it will be like moving from here to 150, 160, 184, 18, 38, 39, 55, 58, 90. I hope this is clear. If not, I'll try to make it a little bit like that. Alright? So that's the head moves. I think the algorithms are like, simple enough to just find out what to do. If it was a C-scan, we also had to do an extra, U-turn here, going all the way to the end and come back. And we didn't care about the cylinder move if the last request was here, but here it was not. If it was a C-scan, we had to again do a U-turn around here and come back. It's just like a waste of time there. So this was if it was a C-scan. Alright? So, for counting them, we just add them up, and it's sometimes they cancel each other out, so don't add them, just to each other. Usually they cancel each other out easily. So, and this actually I'm going to show you here. So, if you are at 100 and you want to move, from 150 to 100, you are basically moving this much, right? And then you move 150 to 160, which is, the movement is 160 minus 150. And now you move from there to 184. You basically move from 184 to 160. Right? And as you can see, obviously, these will just go up. Right? So the reason is, whenever you want to count this cylinder movements, the direction, as long as the direction doesn't change, it doesn't matter if you stopped on the way or not. Right? We're not counting those latencies. So the head movement, the cylinder movements, is basically from 100 all the way to 184. On the way back, again, from 184 to 18, right? That's 162. Now, if you were stopping all the way, if you were C-scan instead of a C-look, if it was look, you would probably pick these up on the way, right? It doesn't matter. The head movement, the cylinder movement that you make is from 184 all the way to 18, right? But when you change the direction, you have to make sure that you add up. So basically what we do here is 184 minus 100, that's 84 going up. And then from 184 minus 18, which is 162 on the way down. And then again we make a turn and we go from 90 negative minus 18, which is 72. And then you basically add these up. So you have, what is that? 4 and 4, 8, 4 and 11, and then you have 218. No, 300. Oh, I didn't add that up. Ooh. I didn't thought that I make that much mistake in this. 8 and 6 and 14 and 17. Yeah, 21. Just wanted to double check not to make a mistake. Alright. That's it. So if it was a C-scan, it would just like add up this much. What is this one? Like a loop around this one is like 15 and back 30. So you would add 30 here. If you add a C-scan, again, you had like 18 and 18 back here, so that would like be 36. So 66, you add it up, and you get like 84. That would be if it was a C-scan. Right? If it was a first come first serve, then that would be a little bit harder because you would like keep changing rotation. So you could not do this, that bundling that we did here. It would have been a mess. You have just to write it down and just like add up. It could get a little bit messy. The shortest seek time also might have like obviously more direction changes, but overall, I mean, it's the same. So this might be a little bit like a long request queue, but if it was shorter, it would be easier. Yeah.
Do they do anything with two heads? So like as the one head moves towards 184, the other head is like starting to align over there?
No. I think I haven't actually, seen or looked into the different technology of different hard drives. But as far as I think the ARM actually the ARM don't move like that. I think the ARM assembly moves like this, so they cannot basically address two different cylinders.
You can't put a second ARM on there?
I think the ARM is already there, as one of the students asked, but I think that's just like to cover two sides of the platter like that. So
you couldn't have two heads to read down the same side of the platter? Because one head like moves towards 199, the other head starts at the beginning, and then there's no transfer moving all the way back. You can just pick up on the second head.
And then what happens if they go on and cross each other?
Well, would they be on two separate sides of the disc? It's like if you have a disc.
Oh, you want like these? Well, that's like a lot of.
They're just moving.
Yeah, I see what you mean. Then there's a lot of extra manufacturing into it, right? Now you have a whole ARM assembly on this side and a whole other ARM assembly like that side, right? Why would you want to do that? To speed up? Then you have no. That's a good point. That's a good point. But then it doesn't make sense for manufacturing purposes. If you want have two accesses like that, then you don't do it on one hard drive. You RAID two hard drives. That gives you the same idea. Two different locations, and then you parallel the data, but you do it logically in the not on two different hard drives. Your file system handles that. Splits every other sector separately, so on your sequential data, whatever happening, right? So that's what RAID is, and we're going to cover it actually in the next session. RAID. You can get much more data speeds, because if you add the second one, the question is why not the third one? Right? You can always go, but that especially because it's a physical component, it has errors, it has weight, it has price, whatever. It just doesn't make sense for them. Right? And usually, again, the software can make up for it, with file allocation schemes and whatever. So.